Hello, welcome to YouTube channel scientific underscore math and welcome to this lesson solving system of linear equation using iterative method. Okay, so in this lecture we will solve an example using the iterative method, that is the Jacobi iterative method. Okay, so an overview or the introduction of iterative approach was discussed in the last lecture. If you have not watched those lectures, then you really need to go back and watch those lectures. Link is available in the video description. Okay, so introduction to the iterative methods we have already discussed in the last lesson, and the condition for convergence also studied in the last lecture. In this lecture, we will only solve example using the uh, mm, Jacobi iterative method, and in the last lecture we have also discussed the difference between Jacobi and the Gauss-Seidel method. Okay, so let's start to solve example using the Jacobi iterative method. Okay, solve the following set of four linear equations using the Jacobi iterative method. Okay, so we have four linear equations, and we know that what we will do first. Okay, so our first step is uh, we write the system of linear equations in the matrix form. Okay, so we have the matrix form is like that, and after writing them in matrix form, we will check the given matrix is the given coefficient matrix is diagonally dominant or not. Okay, so we have also studied in the previous lectures uh, about the diagonally dominant matrix, how the matrix is diagonally dominant. Okay, and how we can check the given matrix is diagonally dominant or the given matrix is strictly diagonally dominant. Okay, so I will provide the link in video description. You can watch those lecture. Okay, so let's go forward, and we check whether the coefficient matrix is diagonally dominant or not, and we know how we can check. Okay, so first we add up all these uh, values, and then we will check whether the sum of all these terms is greater than or less than uh, less than the diagonal element. Okay, so so we can see that the absolute value of the diagonal element, that is 9, is greater than or equal to the sum of absolute values of diagonal entries or the of diagonal terms. Okay, so here we can see that 9 is greater than the sum of all other terms, that is 7. Okay, so similarly for next diagonal entry, that is 8, and next the absolute sum of the off diagonal entries, and which is equal to also 7, and that is the less than the diagonal entry, that is 8. Okay, similarly for this one, and in this case we also see that this one is again the diagonal entry is greater than the sum of absolute values of diagonal entries. Okay, so similarly for this one, and this one is also true. This means the coefficient matrix is strictly diagonally dominant. Okay, so our first condition is fulfilled, and note that the given system satisfies the convergence criteria. Okay, it may be written in explicit form. Okay, now we write all of them in explicit form like that. First we have x1 is equal to 1 by 9 and 54.5. Okay, minus 2x2 plus 3x3 and plus 2x4. Okay, so this one is the explicit form. Similarly for x2 and x3 and x4. Okay, so we have explicit form of all of them like that. Now we write them in kth form, k plus 1, 1th form. Okay, so we have the iterative formula for that like this one. This one is the k plus 1th form, k plus 1th. So we have this one is the iterative formula. Now we substitute, we put the initial solution or the initial guess in this in the right hand side of this all equations, and after solving or after simplifying, next we will get the uh, second estimated solution. Okay, so we will calculate the initial or the first estimated solution by using this formula. Okay, so we can also take the initial solution like all to be zero, all can be zero. But if we calculate the initial guess by using this formula, then the solution will uh, faster converges toward the exact solution instead of if we take the initial or the estimated solution zeros. Okay, so we will use this formula and we will calculate the initial solution by using this formula, and we use these initial solutions to calculate the next iterative or the next estimated solution. Okay, so we have the first one is this initial guess or the initial estimated solution. This one is the second, and this one is the third, and this one is the fourth. Okay, so next we substitute all these in the equations, and in this column we will see there will be the iterations, and in this column we substitute the values of the estimated solution, and in this column we will see there will be the relative error between the previous and the next iteration. Okay, so we have the all of four equations in explicit form for k is equal to 1. Okay, so we can see that this one the first iteration, and this one is the first equation, second, third, and one is the fourth. Okay, so now we substitute the values of x11, x12, x13, and x14. Okay, so we can see that this one is the x1, x12, x1. Sorry, this one is the x12, x13, x12, x13, and x14. Okay, okay. So after simplifying and these values, we get the new estimated solution of x21 is this one. Okay. So next, for x22, uh, okay, we substitute the value of x11, x13, and x14. Okay. So after simplifying this one, we get the new estimated solution, that is the x22 is this one, and similarly for x23 we substitute the value of x11, x12, and x14, and after simplifying we get the new estimated solution x23 is this one, and similarly for x24 we have new value. Okay, this one. Okay, so now we calculate the relative error, that is the in next iteration minus the previous one. Okay, so for k is equal to 1, that is the first iteration, and for I is equal to 1, 2, 3, and 4. Okay, so that relative error is this one. We can see that here we have x2 minus x1 divided by x11. Okay, so this means we have x12, x11, and x11. In this one, we have the new estimated solution, that is this one, and this one x11. This one is the previous estimated solution that we have calculated using this formula, that is this one, and divided by again this value. So we have the relative error, this one. Similarly, for next, this will be x22 minus x. This one we have x22 minus the previous one is x12. Okay, so here we have x22, okay, and minus x12. And similarly, for this one, x23 minus x13 divided by x13 and x root of this value. And for similarly for fourth one, x24 minus, similarly for x24 minus x14 divided by x14 and x root of this value. Okay, so this is the way we can calculate the relative error, and this one is the first iteration. Now we will move forward toward the iteration 2, and we will use all these new estimated solution. Okay, so we have iteration number 2 for k is equal to 2, and here we have the system of four equations, and we substitute all values like x21, x22, x23, and x24 in these equations to calculate the new estimated solution like x31, x32, x34, and x33, x34. Okay, and similarly we will calculate the relative error. Okay, so we can see that after substituting the new estimated solution x22, x23, and x24 in this equation, we get the new estimated solution x31, and like this one 4.9189. And similarly we substitute the value x21, x23, and x24 in this equation, and after simplifying we get the new estimated solution, that is x32, and similarly for x33, and similarly for x34. Okay, so on the same steps we will calculate the relative error for this iteration also, and we will see the the error will be reduced as we move toward the number of iterations. Okay, so this one is the iteration number 3 for k is equal to 3, and these are the four system of linear equations that are arranged in explicit form, and again we will substitute all these new estimated solution in these equations to calculate the new estimated solution like this one x41, x42, x43, and x44, and on the same steps again we will calculate the relative error. There will be k is 3. Okay, there will be 3. Okay, and we will calculate on the same steps and, as we have already done in the previous iteration, and we will calculate the relative error. And okay, so we can see that we do iterations until convergence has been obtained, and the iterations is terminated or the stop until the convergence has criterion is satisfied, means the relative error should be less than any given tolerance or the epsilon, that will be maybe 0.0001. Okay, this one is the allowable error or the tolerance in the uh, in our given solution. Okay, so let's see the convergence of the system using NDT Lab. This one is the software that I have developed, and you can download the software. Video link is available in the video description. Okay, so here we have the number of iteration, 4 iteration we have done, and we okay, we can see that after some iterations the solution is converging toward the this one toward 5 to 2.5 and -1, and we can see that where the tolerance or the allowable error in the solution is 0.001. Okay, so after achieving this tolerance or this error, we can see that the iteration is solved and we have the solution or the estimate solution. We have this one, the x1 x is equal to 5 and x2 which is equal to -2 and x3 which is equal to 2.5 and x4 which is equal to -1. Okay, so we have the solution of system of linear equation is this one, 5 -2, 2.5 and -1. Okay, you can download the NDT Lab software. The link is available in the video description. Okay, so now we can plot the error. Okay, so we can see that this one is the graph of the or the plot of the error. We can see that the error is decaying as the number of iteration is increasing. In this on the x-axis we have number of iteration and here we have a error on the y-axis error value. Okay, so we can see that as the number of iterations, as the number of iteration is increasing, the error in the solution, the error in the solution is decreasing or decay with the number of iteration and become 0 or 0.0007 nearly equal to 0 after 17 iteration. Okay, so this is the Jacobi method, and you can watch the earlier lecture. What is the difference between the Jacobi method and the Gauss-Seidel method? And in next lecture, we will solve example related to the Gauss-Seidel method. Okay. So thank you so much for watching my video. Please subscribe my channel scientific underscore math for more videos.